Example 7. Part 1, we want to show that x to the power of n times 1 plus x to the power of n times 1 plus 1 on x to the power of n is equals to 1 plus x to the power of 2n. Now, part 1 is not too bad because it's fairly easy to prove if I just take the x to the power of n and the 1 plus 1 on x to the power of n, and if I join them together, right? Because you can see that they're both raised to the power of n. So if I check out part 1, we can say that left-hand side, which is equals to x to the power of n times 1 plus x to the power of n times 1 plus 1 on x to the power of n, right? We can rewrite this as 1 plus x to the power of n times, and then I've got x to the power of n, and I've got 1 plus 1 on x to the power of n, so I'm going to rewrite this as x times 1 plus 1 on x to the power of n, right? So I've taken the power of n to the outside, and on the inside, if I clean the expression up, you guys can see that x times 1 is x times 1 on x is 1, right? So I've got x plus 1 raised to the power of n. 1 plus x to the power of n, x plus 1 to the power of n is therefore the same as 1 plus x to the power of 2n, which is equals to right-hand side, okay? Now, that being said, part 2 then wants us to hence prove that 1 plus nc1 squared plus nc2 squared plus plus ncn squared is equals to 2ncn, which is equals to 2n factorial over n factorial squared. So when we look at this, right, if I look at the expression 1 plus x to the power of 2n, okay, I need to look at this because I've got this binomial coefficient for 2ncn. And it should be quite obvious that 2ncn is related to 1 plus x to the power of 2n, right? Because if I take a look, right, part 2, at 1 plus x raised to the power of 2n, and if I expand this, what we're looking at is, of course, 2nc0 plus 2nc1 times x plus 2nc2 times x squared plus 2nc3 times x cubed, and you guys know how the pattern goes, right? And from this, if I want to examine the coefficient for 2ncn, hopefully it's quite obvious that 2ncn is going to be equals to the coefficient of x to the power of n in 1 plus x to the power of 2n. Okay, so that's obviously extremely important. That's going to be our starting point, right, for proving this binomial identity, right? So 2ncn is the coefficient of x to the power of n in 1 plus x to the power of 2n. So how is this going to relate to what we actually want to prove? If we come back to the identity that we want to prove, right, which is 1 plus nc1 squared plus nc2 squared plus ncn squared, right, we know the significance of 2ncn, we know what it means. So if I take a look at the left, right, we can see the left-hand side has a lot of terms, quite a mess. And I've got the 1 at the front, but remember that 1 over here is really just nc0. And if I want to try to fit into the pattern, if I know that nc0 is 1, then of course nc0 squared is also 1. So apparently the pattern that we're looking at is going to be nc0 squared plus nc1 squared plus nc2 squared plus all the way to ncn squared, right? Of course, ncn is also equals to 1. Now, that being said, if I'm dealing with this whole sum of binomial coefficients, we know that nc0, nc1, nc2s and stuff like that, they obviously have something to do with the coefficients of the expansion for 1 plus x to the power of n. And when I look at the working out that we have in part 1, we know that 1 plus x to the power of 2n is equals to 1 plus x to the power of n times x plus 1 to the power of n. So in this case, this is actually where I'm going to start from, right? So if I take note, 1 plus x to the power of n, okay, times x plus 1 to the power of n, right, which we said that is equals to 1 plus x to the power of 2n. If I take a look at this, we know that if I expand, right, for 1 plus x to the power of n, we're looking at nc0 plus nc1x plus nc2x squared, and we know that we're looking at ascending powers of x plus, and we know that this continues, right, until we get to ncn x to the power of n. But I want to write down a couple more terms than just the last term by itself. So we know that, for example, the third last term is going to be ncn minus 2 x to the power of n minus 2, and then we've got ncn minus 1 x to the power of n minus 1, and then we've got ncn times x to the power of n, okay? And this is going to get multiplied with x plus 1 to the power of n, which we know is going to expand into nc0 times x to the power of n plus nc1 x to the power of n minus 1. And what we've got here, right, are descending powers of x, right? Because we switched from 1 plus x to the power of n to x plus 1 to the power of n, where x is the first term, right? But the pattern is pretty much still very obvious. And then the next term is going to be nc2 x to the power of n minus 2. And then we know that this is going to continue, right, to ncn minus 2. And then it's going to be x squared plus ncn minus 1 times x. And then the last term is just going to be ncn as a constant. Right? And this is perfect because when we look at this expansion, the way that we wrote this couldn't have been better, right? Because you guys can see that if I'm multiplying every term in the first bracket with every term in the second bracket, and if our focus is on the x to the power of n term, right? So let's ask ourselves, if I take every term in the first bracket multiplied with every term in the second bracket, how do we get the x to the power of n term? Well, I can take the constant in the first bracket and I can multiply that with the x to the power of n in the second bracket. That's going to give me an x to the power of n. I can take the x term in the first bracket and multiply that with x to the power of n minus 1 in the second bracket. Okay, that's going to give me an x to the power of n. I can do so with x squared times x to the power of n minus 2, right? And then we take this relationship, we continue forever, okay, until the last couple of terms. We've got the x to the power of n minus 2 times x squared, x to the power of n minus 1 times x, right? X to the power of n in the first bracket times the constant. So we've got n terms altogether, okay? We've got n terms through the product of the terms in the first bracket with the terms in the second bracket. That's going to give us an x to the power of n term. So in other words, the coefficient of x to the power of n, okay, the coefficient of x to the power of n in the expansion for 1 plus x to the power of n times x plus 1 to the power of n, that is equals to nc0 squared plus nc1 squared plus nc2 squared plus all the way to ncn minus 2 squared plus ncn minus 1 squared plus ncn squared. And of course, the only difference here is from the question, we just want to take the nc0, and we know that that's really just equals to 1. So, I mean, 1 squared is really just 1. So 1 plus nc1 squared plus nc2 squared plus dot dot dot, right, to ncn minus 2 squared plus ncn minus 1 squared plus ncn squared is the coefficient of x to the power of n in the expansion of 1 plus x to the power of n times x plus 1 to the power of n. And since this expression over here, right, since this expression is identically equals to 1 plus x to the power of 2n, then when we expand these two expressions, they must have the same x to the power of n term, right? So 2ncn, which represents the coefficient of x to the power of n in the first expression, must therefore be equals to, right, the 1 plus nc1 squared plus nc2 squared plus dot 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 all the way to ncn squared, which is the coefficient of x to the power of n in our second expression, right? Given the equality of the two expressions, 2ncn must therefore be equals to all of this. Okay, so writing out our conclusion, okay, what we're looking at is since 1 plus x to the power of 2n is equals to 1 plus x to the power of n times x plus 1 to the power of n, right? The two expressions must have the same x to the power of n term, okay? Which is why 2ncn is equals to nc0 squared, right? Which is also 1 squared plus nc1 squared plus nc2 squared plus dot 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 all the way to ncn squared, right? So that's how we equate the coefficient to prove that. And of course, in this case, we also want to show that this is equals to 2n factorial over n factorial squared. So what this means is if I take 2ncn, we should know that 2ncn is equals to 2n factorial, okay? We keep the bracket around 2n because the factorial belongs to the 2n as a whole. It's different to say, like, if I rewrite it without the bracket, because this is saying 2 times n factorial, Okay, so make sure we don't write it like this. It's going to be 2n inside the brackets, and then it's going to be factorial, and then this is going to be divided by 2n minus n factorial times n factorial, which we can see is just 2n factorial over n factorial times n factorial, okay, which is what gives us the 2n factorial over n factorial squared. Okay, so naturally, 2ncn is equals to all of this, the sum of the binomial coefficients on the right, which is in turn equals to 2n factorial over n factorial squared. Okay, so that's what we're looking at for this particular question. Now, just before I leave it here, I have a final remark, and that is beware of the situation, right, when we have 1 plus x to the power of n times x plus 1 to the power of n, because some people, when they look at this, okay, they go, okay, I've got 1 plus x to the power of 2n, right? And in this case, I was very specific about writing it out as 1 plus x to the power of n, right, times x plus 1 to the power of n, because some people might not realize that. Okay, I did that on purpose, because if you did this by writing it as 1 plus x to the power of n times 1 plus x to the power of n, what you'll realize, okay, is if I do the expansion for both, okay, I'll do this. So if I've got 1 plus x to the power of n times 1 plus x to the power of n, this is going to be equals to nc0 plus nc1x plus nc2 x squared plus dot 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 plus ncm minus 2 x to the power of n minus 2 plus ncm minus 1 x to the power of n minus 1 plus ncn x to the power of n multiplied, right, with exactly the same thing. X plus nc2 x squared plus dot 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 ncn minus 2 x to the power of n minus 2 ncn minus 1 x to the power of n minus 1 plus ncn x to the power of n. Okay, so this makes it a little bit more difficult, because if you are trying to hunt for a pattern here, right, because remember the expression which we want to show is the nc0 squared plus nc1 squared plus nc2 squared plus dot 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 all the way to ncn squared. But if I try to hunt for that pattern right now, the nc0, right, times nc0, nc1 times nc1, nc2 times nc2, so forth and so forth, that is actually not going to give you any nice patterns. Do you see that? Right? nc0 times nc0 is going to be the constant term. nc1x times nc1, that's going to be the x term. nc2 times nc2 is going to give me x to the power of 4. So that's no good, right? If I do this, sure, I get the binomial identity for nc0 squared plus nc1 squared plus nc2 squared and so forth, but we can't equate anything, right? So therefore, if we don't do this, okay, and obviously we realize that we can't equate anything, and then we go back to drawing board and then we think about this again, right? They go, well, what is the obvious relationship to do here? And you guys notice that I started off part 2 by identifying that 2ncn is the coefficient of x to the power of n, right, in 1 plus x to the power of 2n expansion. So if you go, okay, let's look for the x to the power of n expression over here, which is the correct thing to do, right? Then we take nc0, which is a constant in the first bracket, times x to the power of n in the second bracket, and then we've got the x term in the first bracket, times x to the power of n minus 1 in the second bracket, right? You take the x squared in the first bracket times the x to the power of n minus 2 in the second bracket, right? And just let this continue. You will get the identity for getting the x to the power of n term from this particular expansion, but it's not going to look as nice, because what this will turn out to be is coefficient, right, of x to the power of n in this case is equals to nc0 times ncn plus nc1 times ncn minus 1 plus nc2 times ncn minus 2, and the pattern continues, right, until we reach the last one, which is ncn times nc0. And in reality, okay, this is actually exactly the same as the one that we proved over here, right? The 2ncn is equal to nc0 squared plus nc1 squared plus nc2 squared all the way to ncn squared, right? But it doesn't look the same. Okay, but we can turn this into what we want by taking note that nck is equals to ncn minus k. So ncn, right, by definition is exactly the same as just nc0 right? And I've got NC1 times NCM minus 1, but NCM minus 1 is exactly the same as NC1 plus, and now I've got the NC2. NCM minus 2 is exactly the same as NC2, and so forth, right? So we arrive at the same expression, but at the end of the day, we arrived at the same expression through a lot more work. Okay, so that's obviously very important. So that's one trick to keep in mind. Sometimes if you don't actually have the correct alignment, okay, it makes things just that much more difficult. But also keep this identity, right, at the back of your mind. It's fairly important. NCK is equals to NCM minus K. Sometimes we do need to make algebraic manipulations so that the identities work out. So keep these tricks at the back of your brain. Okay, so that being said, watch out for things like this, right? Try a lot of different things. Remember, at the end of the day, identity work is just really a lot of algebraic hands-on. So you're just going to practice and practice and practice until you're, familiar with all the little tricks associated with this aspect of the work. Okay, so that being said, this concludes example 7.